I'll start by making another joke, which is that it's not a slip on David's part that he mentioned this award that he was about to say that I won last year, because the announcement was last year, and then you get all sorts of emails about it. And then I went to the meeting of the ACS meeting in March, and that's when they actually gave me the award. And then I went to a meeting in San Francisco, and they gave me there was a symposium. So I feel like it was the award that just kept on giving. And it's probably okay because it's likely the last award I ever receive, right? So you might as well get as much of it out of it as you can. So it was not a mistake that it was last year and this year on your part, David. Thank you for the very kind introduction. What we're going to talk about today is the structure and dynamics of pattern nanospheres. This is one of a number of projects that we work on in my group. I've got this is a few of the pictures, a picture of a few of my students in our day lab. Once a year we get together for a group pool party, and because it is they do a number of different systems or we study a number of different things. I wanted to just give you a quick taste of some of the other projects that we work on, so I can highlight some of the students that are here as well in the audience, and then I will talk to you in earnest about nanospheres. Okay, so the first thing is I want to mention that we, on the sort of the most physics-based approaches that we work on, we've been studying reaction rates of small molecular systems. Galen Craven, I don't see him in the audience and he's not waving, has been doing a very nice job trying to address how you can use transition state theory. And transition state theory, you might remember from your chemistry classes, is the way to describe chemical reactions very simply and quickly, just by knowing what the barrier is, energy barrier is, or free energy barrier is. There's a small correction, sadly a small correction due to dynamics. I say sadly because my whole career has been trying to understand the dynamics of these chemical reactions, and that's a correction over the Arrhenius rate, Arrhenius energy that gives rise to the rate. And so we've been using or developing a transition state theory that's not approximate but exact. And under which conditions is it true that we can obtain exact reactions? So he's been working on that. Dr. Ashley Tucker, who was a graduate student in my group years ago, worked on understanding structured solvents. And these are solvents rather than our nanospheres. So we're going to talk about nanospheres, and we're going to decorate these nanospheres and ask, how does the decoration on the nanosphere give rise to interactions with other nanospheres? In that little bit of tickling due to that decoration, what kind of assemblies do you make, and how does it relax? What is the dynamics of it? So imagine you are all little nanospheres. You have orientation because of your heads. They tend to point in a direction, and they sometimes align. Right now they're all aligned in this way. So you're not affected at all by your neighbors in terms of how you are arranging yourselves, because you are responding to the external field, the speaker, in terms of your alignment. But if I were to remove the speaker, how would you suddenly start aligning? Well, if you are like most people, you start to change your heads and start talking to people around you or behind you. And then there wouldn't be a net orientation, right? So the question is, how does that decoration on these nanospheres give rise to structure and relaxation? That's what we're going to talk about today. Another way that you could ask that tickling, instead of a nanosphere, which can rotate on its axis in any direction, what if it was physically structured? So it was a tube, and so we had a number of tubes, and the tubes gave alignment, and you can ask what is the relative alignment of these tubes, as well as what is the diffusion of a particle through those tubes. Can you control the diffusion by controlling the alignment of the tubes? And that's work that Dr. Tucker did. Again, picking on the theme of interactions, our interactions can be hard, or they can be soft. If they're hard, particles bounce, and they behave differently than soft interactions. Now this was soft, but it was only because I could feel his aura that I knew to come back. But in real particles, they have interactions due to charges and, let's say, dipole-dipole interactions, etc., which give rise to, depending on the energy in which they come in at, that it gives rise to them penetrating more or less, changing the collision frequency. So, but it's a lot easier to describe hard particles like billiards than it is to describe soft particles. And so with Galen Craven, we've been developing models where we can use hard particle interactions, but with stochastic, in a stochastic way, to mimic soft particles. And so that's the job that Galen has been doing. We would then move into thinking about proteins. Haley Bureau, who is in the audience, taking up some work by Gungur Ozer, who was a graduate student in my group. We've been trying to understand proteins and the energetics of those proteins. It turns out that the fundamentals of how that happens, we started to understand using, funnily enough, non-equilibrium methods. So you can imagine proteins moving around, pulling them apart, and still be able to calculate the free energy, even though of equilibrium, even though you did it under non-equilibrium conditions. And that's become of such interest to us that we're now trying to apply that to a number of systems. So Dr. Kaylee Allen, who may be in the audience or not, as well as Dr. Ellie Hershkovitz and Ryan Bucher, who is in the audience, I see him there, are all working on different proteins, peptides, and also different ways of perhaps make that computationally efficient. Another project is, and that was in collaboration with Kimberly Clark, who I hear is visiting us today. I doubt that any of the Kimberly Clark people are in the audience, but we'll wave hello to them in the other room. Then working on a project in the Air Force. This is a collaborative project with an electronic structure theorist at UT Austin, a mechanical engineer at Michigan, and an aerospace engineer who does experiments, shock tube experiments at Stanford. We're trying to understand non-equilibrium air. You might think, what is non-equilibrium air? Is it the air that's coming out of my mouth? That's out of equilibrium. And certainly is out of equilibrium compared to the atmosphere, because I've changed the composition while it was in my lungs. And we can ask what the relaxation of that is. But that's not a very interesting non-equilibrium air, because it's going at relatively small speeds and isn't changing the chemistry of the environment very much. What if the air was moving at between Mach 2 and Mach 10? And what if, as a consequence of that, it was going across materials that it was reacting? What can we then start saying about heat transport and energy transport across that material, as well as composition across the material? So that's what we're working on with Dr. Ingo Lusoy, who's been looking at some of the fundamental aspects, including crazy questions about roaming, as well as with Alex Popov, who is not in the room. And then finally, an altogether different project, and this is the Open Chemistry Collaborative in Diversity Equity with Dr. Shannon Watt. We and a number of others on our board, we've been trying to help the chemistry community be a more accommodating environment to people along multi-ordinate degrees of freedom. What are these multi-ordinate? It could be African American, Hispanic, female, could be foreign, it could be first-generation scientists. There's many different ways in which we're diverse. And adding that diversity, being inclusive, should give rise to a successful scientific enterprise. And so we're working to try to move in that direction. So that gives you a taste of some of the projects that we're working in. Today I'm going to talk to you specifically about surface structured colloids. And an example of this you see here from a 2008 paper in the Journal of Material Chemistry. And the idea is you have some molecules, but at some coarse grain level, much, much larger. Oh, I move away from the slide, and then probably the person with the camera, is the camera just pointing at me, or is it pointing at that? Oh, so it doesn't matter where I am. Good. Because I want to be able to be with you guys. And also, as I start walking with you, it makes it harder for you to fall asleep. So not to mention that by changing your body position, it helps you learn better. A seminar should be about learning, right? Or should it just be about me talking for an hour? I'm not sure. I think most people do the latter, but I'd rather do the former. So we have some molecule, some coarse grain structure whose surface is characterized by some kind of moiety with different types of interactions, as you see there. And that gives rise to some structure, maybe a crystal, maybe a solid, or maybe an amorphous material. And the question we want to ask is, depending on how we decorate the surface of the particle, what does it give rise to? And the simplest way we could decorate it is we could not decorate it at all. We could just have the same material on the surface. We'll call those green particles. I don't know why green, inert, I don't know, sustainable, I don't know, but it's the same. Spherically symmetric. Red, blue, just two different colors that are not green. And now with and I can make half of it, the one hemisphere red and one hemisphere blue, and we'll talk a bit about what that means. But now I have at least some decoration, and I can ask, how does that decoration work? Or I could put triangular patches, I could make tetrahedral patches. These tetrahedral patches are kind of cute because you might imagine if these two were positively charged and those two were negatively charged and the blue was inert, that starts looking like water molecule. Kind of a funny water molecule. And you could ask, how does that water molecule structure give rise to the structure we know of water? That's at a very small length scale, a few angstroms. How is that similar to if we start looking at decorated particles that are maybe hundreds of nanometers or thousands of nanometers or millimeters in diameter? Still perhaps the same physics if I can treat these moieties as spherically symmetric just with those patterns. So, well, a colloidal system, and I don't know who drank milk this morning? Only two of you? Want to admit it? You drank a colloidal system. Did you get poisoned by it? No. So we are used to having and drinking and seeing colloidal systems in our everyday world. And what it is simply a non-homogeneous solution that has a liquid phase and some particle phases floating in it. Probably in most, as you know, the milk solids, they're not all the same. There is a polydispersity in the size of that colloidal distribution. So you're used to thinking about a non-monodispersed sample of colloids. We're going to, and here's an example of it where these colloids are 200 nanometers, and we're used to asking what are the phases it gives rise to when they are spherically symmetric. Right? No decoration on them. What we're trying to ask is, what if you could decorate those colloidal particles? Would anything interesting come about? And so these Janus colloids, where half the spheres are coated in with one material, the other half are another material with some overall diameter, some relatively large length scale, and the relative interaction, and this is one key point that will come back again and again, the relative distance of the interactions between these particles is very, very short. That's completely different than the water molecule example. When I told you about the water molecule as an example, the diameter of the water molecule was on the order of the distance for interactions to its neighbors. 2 or 3 diameter distance over, there's still some interaction between those water molecules. Whereas in these, the interaction to the next particle is only a small fraction of the diameter. They only feel a little tickle from the vicinity near the neighboring particle. And there's 2 ways that these particles have been envisioned. There's many, but for which a lot of work has been done. One is where they're positively dipolar, so it's a positive side and a negative side, or amphiphilic, when there's a part that likes water, and there's a part that likes water, and there's a part that doesn't like water, hydrophobic or hydrophilic. We can talk about the amphiphilic systems. There's been work that shows that they give rise to really crazy structures, and even ones where they sort of cluster, but then the clusters have a maximal size, and then there's openings between them. So they're quite interesting, both in terms of looking at how they're formed, and once formed, let's say these sort of clusters, how they arrange. But we're not going to think about those amphiphilic systems because a lot of work has been done on them. We focus instead on the dipolar ones that had received less attention. Can you make them? Right? That's the first thing. If chemistry is makers, measurers, and modelers, I'm on the modeler side, you better be able to make them and measure them. Otherwise, it won't be very interesting if you can model them. Okay, so we're the modelers. You can make them. I can't make them. Someone can make them. One way of making them is using the thin layer method. And you take a surface which is maybe positively or negatively charged or likes one particular surface of the colloidal particles. These latex spheres stick onto them, and then you coat the top half, and now you've made them. Now, there's one small problem with making them this way. Any guesses for the small problem for making them this way? I mean, there's a lot of problems, but what would be one problem if I wanted to actually use these materials? Go ahead.
Low yield.
Low yield. I make very few of them because that surface is only so small compared to my volume, right? So I'm only going to make very few. I make one set, I make another, and at most I might be able to use these to do some cluster experiments. So I want to be able to make a lot. Well, anyone who's ever studied catalysis knows what the trick is. You put the catalyst into solution, right? You make the surface in which you do the reaction be dispersed through the sample. And so what they do is they use a wax colloidal method, where you take bigger colloids, you use those as the surface which you decorate, and then you make a lot more at one time. And so this allows you to make enough of these things to be able to really do cluster experiments, as well as presumably also solvent experiments. And so there's some work showing how they might be made. Much of the literature so far on Janus colloids before our work had been studying the question of how do you even make one of these Janus particles. And we thought that was an interesting question, but it was already being addressed, so we didn't need to do it. What we wondered was, if you could make them, what would they do? Okay. And so here's another example, and they even made some models where you see this big colloid is made of like maybe smaller little effective particles, and we were inspired by that picture for the model potential that we ended up making. So once they make these things, they put them together. What they used for these potentials to make that is they assumed that the particles, let me see, I have it coming later, I'll just tell you now, that the particles either interacted or they didn't. If they were close to each other, they interacted. If they weren't close to each other, facing each other, they didn't. If they were the same color, they were repulsive because they're the same charge. They're different color, they were attractive because they were the opposite charge. But only they went from being interacting to not interacting if there was a particular distance. This is called a patch clamp model. Now that works if what you care about is equilibrium properties, because you can use Monte Carlo methods to obtain the relative structures and compare them to experiment. And they did a very good job of it with those clusters. But the potential that has on-off is discontinuous. Is discontinuity in the potential a problem for doing dynamics? How do we do dynamics? We evolve the equations of motion, Hamilton-Jacobi equations, right? I have a few students from my stat med class, so I want to make sure that they understand. You see, the stuff I was talking to you about, it's really useful. So you're going to evolve these equations of motion. Those equations of motion are like derivatives with respect to position, or derivatives with respect to momentum. Is that going to work if the potential is discontinuous? No, because dv dx at a discontinuity is, what's dv dx at a discontinuity? D, the change of the potential, so potential is discontinuous, dx at a discontinuity. What is that going to that derivative going to be? Infinity, right? That's kind of an infinite force. You don't want to suddenly feel an infinite force because it takes you somewhere very, very quickly, right? And that's going to destroy your numerical simulations. So you can't have discontinuous potentials if you want to do dynamics. We needed to have continuous potentials. So we developed a way of modeling these systems with continuous potentials by basically decorating the surfaces of particles with little beads, having each pair of beads interact with each other through a charge interaction, and that was at long range, that was stipulated by some dielectric, as well as a Leonard-Jones interaction from center to center. Putting that together allowed us to have different smooth potentials depending on the different orientation of the relative particles. The bead-bead interactions, as they come close to each other, they have different potentials. On average, what do we mean by on average? You take the two heads, the two particles, and you rotate them around relative to each other. And each time there's going to be an interaction potential at some pairwise distance. The correct way of coarse graining or doing statistical mechanics says that those that are lower in energy are more likely. So you weigh them through the Boltzmann factor according to the potential. You take that average, and that is some value that is going to be in between, and that's what's shown here. These are the average potentials where I average over all the orientations for different charges or different values of the charge density of these particles. And so we can tune the depth of the interaction potential on average between pairs of particles to be a certain depth. And then what we do is, as I'm going to compare all my particles, the different particles, I always will compare, I'll show you examples for different depths of the potential, but for a given depth of the potential, all of my charges, all the particles that I have will have the same depth. And so that way, whatever structure I find is arising from however I've decorated these particles. And in particular, if this is the average potential, I could pretend these were green particles that interacted only with that average potential. And I can ask, do the green particles behave the same way as the red-blue particles? If the green particles behave as well as the red-blue particles, that means that decorating those particles with red-blue is useless. It does not give you a new material. It does not give you material with new properties. So sorry.
Oh, you're right.
So we wanted to be sure that there was a point to calculating to doing or making these red-blue particles by comparing them to the corresponding green particles. And, well, we had to validate our models. And the first thing was, did they give rise to the same types of structures for the clusters that had been seen earlier by Granik's group? And the answer is it did. And then what we're going to do is we're going to compare the red-blue particles to the green. And this is the picture I was anticipating, where depending on the orientation, you have different pairwise interactions. You average over all of them, and you get the green interaction. With the red-blue particles and the green particles, I can stick them into a container. I can do the dynamics. I can then calculate equilibrium properties, and I can calculate dynamic properties, relaxation, for example. Okay? And I'm going to ask, are these particles any different than those particles? That's the experiment. And I've made the question fair because when I take, for any given red-blue particles that I take, I make sure that their corresponding green particle is the same, is at depth of the potential, the same depth of the potential. So the only difference between these two is, does the tickling that comes out from this close, specific interaction between the red and blue, does that give a change? And so here's the pair correlation function. Now, I don't know how many of you have met a pair correlation function in your life, or if you were to walk down the street and a pair correlation function sneaked up to you and said, hello, would you recognize a pair correlation? I don't know. So let me tell you what a pair correlation function is. What it is you've got a particle standing right here. Now there's a few other particles that are around it. Now these particles, if it's in a solution, they make a kind of a solvent cage. None of them are right on top of me. So right where I am, there's a cavity where there's a 0 probability of finding another particle right on top of me. But at some distance away, there's some probability of finding a particle. Okay, and it's a pretty regular pattern. So there's a peak at that very first solvent shell. Now they in turn don't have someone sitting right next to them, so they kind of have a solvent opening around them. That opening that's around them gives me this little dip. And then the next rise comes from the next solvent shell. But after a while, each of them is sitting down, moving around a little bit, you lose structure, and it just goes to the average probability of finding a particle some distance away. So the pair correlation function tells you what is the probability of finding a particle some distance away from a chosen particle, chosen position. Okay, and the answer is there's a hole, that first peak is a solvent shell, and then there's some structure. If this was a gas, it wouldn't matter. I mean, if it was an ideal gas, it would just be flat. And if it was a real gas, there would be a little bit of a bump, but it would be almost immediately would be straight. And if it was a solid, there would just be sharp peaks at the positions of the regular array. And that's what you're used to from seeing like X-ray crystallography. Okay? So this is something that you may actually have seen before since many of you do X-ray or SONS or other types of scattering experiments. And that's exactly what you measure. You go from your powder pattern, this is kind of like your powder pattern, back and forth. Okay? So, great. So what you see here is, depending on the depth of that typical potential, the typical pairwise interaction. These are particles that are about 200 nanometers deep. Their interaction is only a few nanometers further compared to their size. Okay, you see a solvent shell right near them, and then there's varying structure. And depending on the amount of the packing fraction, whether it's small like 0.1 all the way to 0.4, you get more and more clustering. What is a little bit harder to see from a distance, but you notice I have straight line Janus and dashed line spherical. Straight line Janus and dashed line spherical. Janus are the ones that are structured. Spherical are our green particles. So Janus are our red-blue particles. And you see that you have to be careful, but there's actually some dashes overlaying all of those smooth curves. For the structure, the green particles and the red-blue particles are giving us the same thing. So if all you wanted to do was decorate the particles to get different structures in our solutions, doesn't help at all. Might as well just put green particles because it took a lot of work to make the red-blue particles. Okay, so that's kind of bad news. So let's look at, first of all, why. Okay, so it's always good if you understand science, ask why something happens. So here's our red-blue particle. What I showed you before was the g of r as a function of distance. But we know that for the red-blue particles, there is an orientation. So let me take the red-blue particle, sit on the equator, and ask, as a function of the angle and the distance, what's the probability of finding a particle? And that's what you see here. You notice that there's a kind of a arc there, or sort of a semicircle, where there's a lot of density at roughly the same distance, but there's a little bit of a hole there. That's what's shown here. So we plot what that probability is just along that circular bit. You see the hole, and you see otherwise mostly flat. And so what that's telling us is there's something funny about the edge. The edge is giving rise to a hole. There is some structure that's different, but because most of the positions are on, not just on edge, but across the whole half of the sphere, and it doesn't matter whether you're on the red side or the blue side, it's more or less flat. That's why the green particles are doing so well. Because for the most part, whenever there's a red or a blue whenever there's a particle in contact with another one, they're orienting themselves on average to be the same type of interaction. Now you might be tempted to ask, why don't you do a similar figure for the green particles? I can't do a similar figure for the green particles because the green particles have no interesting equator. Right? No matter where I cut the green particles, it's green on the top and the bottom. And so if I were to do it for the green particles, I really would get a straight line, because it doesn't depend on where I am. So the downside of having the green particle is that I have coarse-grained orientation for my red-blue particles. I no longer have a net orientation. Without a net orientation, I can't look at relaxations. I can't look at any observable related to orientation of the particle that I could do when I had the red-blue particles. Okay, so keep that in mind because that will come up later. All right, so I just told you all that. And we can look at orientational correlations, and we see that there are interesting orientational correlations. But again, these are only available to us if I have the red-blue particle, because if I have a red-blue particle, I have an orientation. If I have a green particle, I have no interesting orientation. So if the structure is not the same, perhaps the dynamics, the relaxation is different. And so, yes, I can't use the red-blue decoration to tailor structure, but maybe I can use the red-blue decoration to tailor relaxation. That is, the way it behaves, or the way that the device operates. So this is what we did. So we did that. And what you see here is the translational diffusion constant of one of these particles in the solution as a function of the interaction of the electrostatic density on the surface. Okay? And what you see is that the pointwise model, that the red-blue particles behave differently than the coarse-grained particles. So is this an interesting result or a trivial result? Let's step back for a second. Many of you may have seen discussions or talks about coarse-grained models. Anybody heard anything about coarse-grained models before? If not, this is going to be your first time. So when you do coarse graining, why do you do coarse graining? You're doing coarse graining all the time. When you look at your neighbor, do you see all the atoms in their body? Do you think you see any atoms in their body? You have totally coarse-grained all of their atoms and much more, their organs, everything, up to the length scale of maybe centimeters or meter, or on the order of centimeters, where you can see the features on their face. And you don't think of saying that your neighbor is that collection of atoms. You coarse-grain that. You think of your neighbor as that which you see, and then of course, however they behave, the noises that they make from their mouth, that after a while you can recognize different types of people from that too, right? So what you're using is coarse-grained variables to identify that person. And from those coarse-grained variables, you are using those to predict the future. If I have a baseball, that has a whole bunch of atoms, but I can still predict its behavior for that coarse-grained baseball. Okay? And that's helpful because if I had to integrate the equations of motion for every atom in that baseball to know whether it's going to be a 60-mile-an-hour pitch or a 100-mile-an-hour pitch, that would be hard. But it turns out it's hard enough just to do it if it's a single object because it does have some deformation. So then you have to worry about that. But it's still not as hard as having to treat every single atom. You have coarse-grained. In coarse-graining it, you've also given yourself another feature, which is that the time step is no longer the time step that's appropriate for an atom motion, which would be femtoseconds or a little smaller. It's now a time step that's in the order of milliseconds or maybe a little bit bigger than that. And that's enough. So you have, not only in coarse-graining the length scale, you've also coarse-grained the time scale. Given yourself the ability to do a much longer calculation, much longer time calculation. That's what we're actually seeing here. Because what we've done is we've removed degrees of freedom and made it easier to calculate. And so that's happiness. The coarse-grained model can be integrated more quickly. But there is one thing that we lost. If I have a room full of people, okay, room full of people, if I want to go from one end to the other, I have to go through them. So can I walk in a straight line from one end to the other if there's a room full of people? No. But if I coarse-grained all the people into two effective particles, they're going to be bigger, fatter particles. They'll be here. But there's going to be a lot of the times when I'm going to just be able to go from one end to the other in a straight line. So, and being able to go in a straight line means a single time step instead of many little time steps. If I can do that, that means that if I don't do anything with the way I was doing the time scale, it's going to look like I can get there a lot faster. So I coarse-grained, and it gives me an equation of motion that seems as though I'm moving faster. But that's not physically right. That means that I have to, in coarse-graining the length scales, fix my time scales so they are right. When we did this, we didn't fix the time scales. We pretended that it was the same Hamiltonian as before. So the question is, how do you fix the time scales? Well, one way that you fix the time scales is that you literally look to see, based on the diffusion, not this diffusion constant, but based on the response of the solvent. So I have to be careful. I pretend it's like a Langevin system. This is stuff you don't know. But knowing the fluctuations of my environment, I'm able to say something about how effectively it dissipates energy or dissipates motion. I can use that to modulate the time scale that I use. And when I did that with Matt Hagee, we were able to get the pointwise and the coarse grain dead on. Now we've really won because we were in the sense of as long as the variable only depended on the green particles, not on it being red-blue, not being oriented, I can now calculate the diffusion constant much faster because I took away degrees of freedom, and I even get it accurately or seemingly accurately for respect to the diffusion constant, and not just at one value along the whole value. So it's not an accident. That's the power of coarse graining. But the fear is I used one particular observable to understand how to dilate or change the time scale. What if, is that correct for other degrees of freedom, for a different observable? The one that I used here was related to the diffusion constant, so it was the right one to use to get that variable correctly. But if I look at other variables, Sorry, I pressed this too many times, it was slow. So if I look at other variables, I don't have any more slides to say about that. So let me tell you what happens. If I look at another variable, like a different structure, and look at the relaxation of that different structure, what's the different structure? The clustering of the particle. So I have, maybe I have 5 or 6 or 8 or 10 or 20 particles that cluster together, and how long does that clustering persist? That's now a many particle observable, not a single particle observable. And we found that when we looked at the relaxation of those clusters, it did not give us the same answer with the red-blue particles as the green particles. Okay. It also, even with the green particles, appropriately transformed. Now the mistake there, or the reason that that could be the case, is one, that I can't just do the simple rescaling of one according to one time, or it could be that the red-blue structure actually matters. Okay. We do believe that the red-blue structure actually matters because of the fact that at least with respect to looking at orientations, we can see relaxations there, and they are quite different, and they vary depending on the density. So long story short, at least with higher order degrees of freedom, higher order many particle functions that involve time, we can in fact modify the red-blue interactions and use that to give us different material properties. Okay, so that's the take-home message. Second take-home message is, if that's true, then why not make stripes? That is, we just had our Janus particle, and that's like 2 stripes, but I could take a sphere and have multiple stripes with exchanging properties. So this one would be 1, 2, 3, 4, 5, 6, 7 stripes. And these materials have been made. This is an example from Hawker's group, where they can make these materials, put them in a solution, and then ask, what do they do? Now, in this particular example, they were using hydrophilic, hydrophobic. We're going to still continue our charged ones. So our charged ones aren't exactly the Hawker particles. The other thing is that Hawker's group didn't really make spheres, or maybe they made a few spheres, but they also made ellipsoids. And so there's not just a question of the patterns, but also the structure. And so Dr. Svetlana Koklova, who's in my group, she's been working on better understanding the origins of the interactions when we have stripes, as well as the ellipsoidal particles. And so what I'm going to tell you today is just some of the results that we saw with Matt Hagee on the striped particles. And again, we want to be able to see them in a lot of them, not just clusters. Now there's a small problem, which is more obvious in this case. For some solvent fractions, for some interaction strengths, you don't have a solution, you get these sort of voids. You get a kind of inhomogeneous phase. That's interesting, but it's also harder to deal with. Why? Because if the length scale of those voids are on the order of our sample, I need to have a larger sample. I need to have a larger box, because the results could otherwise be an artifact of the box size. So we're not going to address this so much for today, or initially, because we were afraid we needed to be sure that we could converge, and already these simulations took a long time. Okay, and so we're going to stay in the solvent regime and just make sure that our systems are in the solvent regime, and when they're in the solvent regime, that's where we're going to try to characterize the behavior. We're going to look at Janus particles, those are the standard ones, ternary particles, etc., all the way to n equals 7. The odd ones are a little bit funny, because you can ask red, blue, red, or blue, red, blue. Okay. Whereas with these, there's blue, red, blue. If you just turn them around, they're the same particle. So there's no problem there. The ternary ones, there's a problem. So what do we do for the ternary ones, or for the odd ones? We just made the choice and just use a neat sample only of that one, at least in the work that we're showing here. In work with Svetlana, what we're also looking to see is mixtures of these ternary particles. As you go from a mixture of ternary particles, red, blue, red, and blue, red, blue, how does that change or matter with how they assemble? So that's one of the projects that we have ongoing. The other question is, how thick should you make the stripes? So if you go back here at Hawker stripes, you notice that when looking flat, they looked at stripes are all the same thickness. But they're not really the same thickness if you were to look along in 3 dimensions, because if it's flat this way, there's a different surface area for those stripes. We wanted to be sure that our particles were net neutral and that all the stripes were contributing the same way. So we made our stripes a little bit differently. The surface area of blue is equal to the surface area of red. So in this case, blue is equal to red, so there's no net. This red plus that red is the surface area of that blue. This blue, in this case, is the same surface area as that red. So in the even ones, each stripe is the same surface area. In the odd ones, they're chosen so that the total red is equal to the total blue. And that means that these stripes are a little bit different. And that, by the way, may be one of the causes of some of the differences in the patterns that we see. Because when they're more equal, they're closer to being the same width when they're even. And when they're odd, the red stripes tend to be thicker than the blue stripes in that case. And so that's one possible origin. You'll see that there's different behavior, some different behavior for some of these than others. And one of our puzzles is why. Here's the corresponding green potential to those pairwise particles. Green, remember, the average potential. And we see that we can get them to be more or less all on the same ones. This is for roughly the same charge densities. We can, well, a little bit of a change, but we can vary the charge density and get them to have the same depth. And when they do, they have the same potential, except for n equals 6. So this guy is different than the others. And we're not sure why. So, and it does have some implications. For example, if you look at pair affinity, where the minimum of that potential is, they all follow roughly the same pattern, except n equals 6. There's phase behavior, I just mentioned. Under some parameters, they form a fluid. Under other parameters, they form a glass. We are afraid of this sort of glassy structure because we're not sure if it's converged, so we're going to only focus on these fluid phases. Nevertheless, we need to know where the fluid phases are. So this is our mapping of our numerical fluid phases versus the other ones. And sometimes the coarse grain model shows the phase transition. Sometimes the pointwise model shows it. And sometimes they both do. Here, for instance, at n equals 7, that phase transition, here's the coarse grain one. And we don't see the pointwise model have that phase transition. But for n equals 2, they were pretty close. So the red-blue particle system really does look a lot like the green one. However, as you move to more stripes, it starts to be different in green. It's kind of odd because I had initially expected that the more stripes I had, the more green it would look like, because you would always be near another red or blue. But what's happening is that if you remember our original picture, that it was only when it was on edge that it was a problem. The more stripes I have, the more edges I have. And so what's really driving differences from being green is the increase in edges. So I can look at the phase behavior, we can look at the phase behavior, and just as before, we do see differences. We do see the velocity autocorrelation function for these systems having some small variations, with the n equals 6 being the most. When we compare the pointwise model to the coarse grain models, without doing the time rescaling, what we see is that the green particles always look exactly like themselves. But the pointwise models, the red-blue, do have variations that change with the number of stripes. And if we were to rescale the coarse grain, we could get it to be dead on to the pointwise model. We didn't bother to do that here. But the take-home message here is that when I have the red-blue particles with increasing stripes, I get different diffusion constants, different structure. I can tailor the behavior by not only decorating them with red-blue, but by choosing how many stripes I have. The structure, by the way, is roughly the same if we were to look at a G of R. This just tells you that there's dynamical accelerations. We can look at the bond durations, and this is now a much more complicated statistic, which just says that it's very different in green. Trying to stay within time, so I think that captured the idea. So what do I want you to take home with? Janus particles, we can describe them with these discrete or continuum representations. The continuum ones can provide similar and accurate results, and they're much faster. Very importantly, we needed to have a continuum representation or a smooth potentials, because without smooth potentials we could not do dynamics. The competition between the interactions at the local scales does give rise to diverse structures that we can tailor, particularly as we change the number of stripes. Coarse graining is interesting, but one rescaling isn't enough. So if you want to develop a coarse graining model, you might want to use this as an example system, a benchmark system, to test your coarse graining. And that's one of the things that we're doing. I sort of start to talk about stripe particles as well. There are unique phase boundaries seen for these stripe particles. When normalized by pair affinity, different end stripe particles do have fluid static structure, just like the Janus particles, but the higher number of stripes leads to slower dynamics. So we can slow the system down while still getting the same structure, and that means we can tailor behavior by using stripes. So with that, I want to thank you for your attention. I want to thank my group in general, but in particular Matt Hagee, who did the work on the Janus particles, and Solana Koklova, who is now continuing the work, and soon we should be able to say some more things about both ellipsoids as well as more details about the interaction of the Janus particles. We have a number of collaborators in other areas. This work has been funded by the NSF and Computing Time on Exceed. So with that, thank you. One and then two. You go ahead.
Thank you for your wonderful presentation. Just wondering, can you give me some example for the application of the stripe particles, because it's quite new.
An example of the application of the stripe particles. Right. So this is actually very early on in the development of materials. Those Hawker particles are some of the first particles that have been made. There's also some particles by Stellacci that there's some dispute as to whether or not they should be considered stripe particles or not, as well as whether they're the right length scales. So there's a few of these materials that have been made. Some of them are spherical, some of them are not. And because of that, they're not yet being utilized in a materials context. Okay, they're not yet been used in the applications. What we're trying to do is ask, do you even want to make them? Right? Because it could be that you made them, and if you knew ahead of time that when you made them they weren't going to have any properties that were any different than the particles you had before, then why make them? Or it could be that the range of differences that they exhibit are not along a tunable range that's of use to you. So what we wanted to do was to ask, if I can study these model systems, do they give me a sense of a range of properties, and what is that range of properties that would make you want to actually go out and make them? Okay, and with the hopes that maybe, of course, the hypothesis was that they would, in fact, be an interesting range. That's otherwise why were the experimentalists doing Edisonian approaches to make them? Okay, but what I can tell you is these latex spheres that I was mentioning before, they've been made. They have not gone, as far as I know, to a device. The Hawker particles are very recent. As far as I know, they have not gone to a device. And what we're saying is, if you make these things, if all you're looking for is structure, then that might not be the most interesting. That you might be doing a lot of work to get something that's not very different than what you did before, unless it gets you into a set of parameters that you could not get to with green particles, but that might be doubtful. So that would be, but if you want dynamics, if your device characteristics and relaxations are tunable and you're interested in being able to tune those, then it might be used, then it should be useful. So that's the take-home message. And Carol.
The part of actually the question was already asked. So what is it? Could you give some real-life examples between the Janus particle that you predicted and the real-life scenario? The protein globule is not Janus, right? There was a point. So could you give any examples?
So the examples I just told you. So those colloidal particles that Granek made, those are latex spheres that are coated. Those have been made. I don't know exactly. I don't remember the details, but we can go look at the papers. The Hawker particles, those have been made. Now those are a little bit of a cheat because they're a bit smaller, and they're done through chemistry. So
this is artificial. What about the real life? Or, for example, can the real aerosol particles be Janus type or the real milk particle? Because it's hard to see where
Right. So there's two different ways in which you could define real, right? One way that you define real is if it's naturally occurring. Another way you can define real is can you make it? Right. So the real that you're asking is are there naturally occurring scenarios which are presently using Janus-like particles? I don't know. Is the answer to that. The kind of real I was addressing was can we make them? Well, I can't make it because I just do modeling. But the makers, I was telling you, can make some of these particles and have used those. If they can make them, then they can use what they made for whatever device they want. So then you might say, well, nature's so good. If it was useful, they would have made it. It's possible.
One interesting example. For instance, if you think about lipid rafts, right? You have the cell and the lipid raft. So clearly, the cell boundary and the rafts can be of a different charges. So if you can play...
Well, certainly, if you think about a cell, I mean, it just depends. It's just how complicated these simple systems. It would be hard. But if you want a complicated one, that I can give you. The one you just gave me, a cell, because the surface, the membrane around the cell, is not uniform, and there's a whole bunch of there's pores. There's a number of things that it does, and that heterogeneity could give rise to the way that the cells orient relative to each other, and that may be the way that they tickle each other, not just through discharges of molecules, although those pores could be the way through which they are discharging molecules. And I'll just say that you could have these cells, and the surface of the cells with the decorations may be what gives rise to different structures. But that starts to be much more complicated than the simple model one that I gave. And so if I were you, I would say, well, that's like apples and oranges almost. But it is an example. Go ahead.
Dr. Hernandez, so in the blue red model or striped model, so it seems the charges is uniformly distributed on the sphere, or it's more localized at the interface.
Very good question.
Also, in the aqueous system, in the water molecule, the dipole is going to do anything important in that system.
A second very good question. So first, let me address the first question. So the first question is, what exactly is this sphere, right? And we don't, in the models that we're doing, we don't worry about what exactly is that sphere. We just ask what is the net effect of whatever is inside of that sphere in the way that it interacts with its neighboring particle. And so we model the fact that there is some net charge which is since we're using charged dipoles, that's uniform in a given region in terms of coding. It's really long length scale, so there's many charges, and you don't have to worry about the fact that you can't make a point charge. Okay, so we're just imagining that there's sort of some net charge, some effective charge, and there's a discontinuity in that red to the blue, but instead of making that discontinuity be on-off, it is a smooth discontinuity that goes from the one side to the other. Okay, so we don't worry about what's actually inside of the sphere and how what's inside of the sphere is giving rise to this interaction. There has been work that has looking at that, and this is I mentioned the name of the guy. There's an Italian guy at Columbia. One of the references Cacciuto. So Cacciuto has done precisely those types of calculations, as well as a few others, and I can give you references later. Okay, but we didn't worry about making them because that's a different problem. Then the second question you ask, which is also interesting, it's actually a tough question, is how do these particles, it's a very tough question in the sense as I explained, how do these particles interact with each other? What we did to make life simple is we assumed that the solvent that's between them was also coarse-grained out. There was an effective solvent, and whatever that effective solvent was doing was giving rise to the effective interaction, which is the one that we're using between them. So we've already used the screening due to the solvent in that pairwise interaction. And so whatever dielectric was there, that was already screening, and that's why it's so short range. If I wasn't screening, it would be much longer range, because charges are very long range. So that's the easy answer. The hard answer is how exactly? So what if I change the solvent? How exactly does it change that pairwise potential? And if you were paying attention, I already pointed out that if I coarse grain, I modify the timescales, and maybe I can get it correctly along for one parameter, but maybe an orthogonal parameter has a different timescale dilation. So if I took those degrees of freedom, have I messed up the timescales in this sort of now mesoscopic model? That could be a problem too. So that's a kind of an ontological question about the model. And that's what Jean Chang, who is here, is one of the problems that he's working on right now. He's a starting graduate student trying to solve the two problems. One is the charge interaction problem, and two, which I didn't even mention, hydrodynamics, which is part of this idea of correlations. Because if I'm in a solvent and I push, even though I didn't touch him, the solvent pushes. And so there's interactions that way. And so we need to include those as well, which we did not. Thank you.
Okay. 1 o'clock.
I'll answer offline.
Yeah, let's thank Professor Hernandez one more time.